Okay, so we are continuing with graphing. We're going to finish up talking about graphing sine and cosine, and then we're going to get into secant and eventually cosecant. And these are normally taught in this order, or it makes sense to teach them in this order. Later on we'll get into tangent and cotangent. But the last thing we had left to do with sine and cosine is to talk about phase shift. I left it kind of vague before, just to not pile too much onto you at one time. But we are there. So just to review a little bit, this is the vertical shift. That's pretty easy. This is the amplitude. That's pretty easy. The period length, 2 pi divided by the coefficient of theta. Well, in this case, the coefficient of theta is 1 over 8. When you divide by a fraction, you actually end up multiplying. 8 over 1 times 2 pi is 16 pi. So just, a rough review of the stuff we've already covered right there. So phase shift. Phase is another word for horizontal, at least in trig it is. So yeah, if you move a graph to the left or the right, it's a phase shift. To find the phase shift, basically, you take the expression that's in these parentheses, the whole thing, and then set it equal to 0 and solve it. So if we want to solve this, we're going to subtract 5 pi over 6. And I didn't really give myself a lot of room here, so you get theta over 8 equals negative 5 pi over 6. To isolate theta, we need to cancel out that 8, so we need to multiply both sides by 8. Theta equals, so you put this over 1, negative 40 pi over 6. And then that'll reduce the 40 and the 6. You can divide by 2, so that's 20 pi over 3. So you get negative 20 pi over 3 as a phase shift. That means that this wave, remember they are that wave shape, has moved left 20 pi over 3 units. That's in radians, pi 3.14, but that's it. So you set it equal to 0 and solve it. A negative answer means that it has shifted to the left. Let me check number 2 and make sure that I didn't just do something wrong. Oh, there it is. Left 20 pi over 3. Let's look at number 4. So again, whatever is in the parentheses, you set equal to 0. That's remarkably similar to the other problem, but it is actually going to work out to be quite different. So add 5 pi over 6. You get 8 theta equals positive 5 pi over 6. To cancel out the 8, you need to divide by 8, or on this side, multiply by 1/8. Dividing by 8 and multiplying by 1/8 is the same thing. So that gives you 5 pi over 48, right? Yes, 6 times 8 is 48. That is a positive answer, so that means that this has a phase shift to the right. Positive meaning to the right. 5 pi over 48 units. Let's check number 4 and make sure. Yep, right there. So that's it. To actually calculate the phase shift, set what in parentheses equal to 0 and solve it. A negative is a left shift, a positive is a right shift. Now, it's possible, and I don't want to get into this too much, but it's possible you learned before about horizontal shifts that they were like the opposite. This might stick out in your mind, that a negative is actually to the right and a positive is to the left. That's if you look here. There's a plus here, which means this is going to be a left-hand shift. You would think positive would be right, but that actually moves it left. And this one you would think a negative would be left, but this, as you see, is actually to the right. So if you have this sort of memory about horizontal shifts always going the opposite, that's if you look at the original equation. But when you go off to the side here and you set this equal to 0 and work it out, we're back to good old normal intuition. Negative is left, positive is right. Okay, so here number 6 is a trig function with lots of stuff, and now we want to find the amplitude, the period or period length, the phase shift, and the vertical shift. So let's do this. We've got amplitude. I'm going to do vertical shift because those are like the two easy ones. I'll come up over here for period length, and then I'll leave space for the phase shift. So amplitude, that's the coefficient of the trig function itself. So the amplitude here is 1/4. This wave is 1/4 the height of a regular wave. Vertical shift is the number added or subtracted that can be in front or after, just not in parentheses. This one happens to be in front, so the vertical shift is, -2. The period length is 2 pi divided by, in this case, 1/2. Well, that works out to be 2 pi times 2 over 1, which is 4 pi. And then the phase shift, this is actually kind of a silly one. Okay, I said whatever's in parentheses, set it equal to 0. There's no parentheses here because there just doesn't have to be, but the angle part, the theta part, right after sine would be that. So you're going to set theta over 2 equal to 0. When you solve this, you still get theta equals 0, which means there is no phase shift in this particular problem. If you look at the one you're going to do for homework, yeah, this one will have a phase shift, and as you can see, it's going to be to the right, not to give you too much, but there it is. Here for number 6, without actually graphing, this is a complete graphical analysis of this sine wave. Amplitude, vertical shift, period length, phase shift. Those are the main parameters of what makes the wave into its distinct shape. So that concludes about everything you need to know about sine and cosine. Now we're going to move into secant and cosecant. And I'm not going to dance around this. We'll just graph it, and I'm not going to try to give you clues and hints and tips. I'm not going to plot points. We're just going to go right to it. So y equals 3, function, trig, secant. Oh, before I go any further, let's make sure that I am in radians and my step is pi. Okay, so this is still good from the other day. So 2 theta, I'm going to use 2x plus pi over 6 minus 2. And that is what that looks like. I'm going to kind of stretch this out from 0 to 2 pi, so it 0 to 2 pi kind of matches the graph paper that we have. And try and get the height there and something that makes sense. So let's see. There we go. So that is a unique graph. Now, what is up with this? Well, these shapes kind of look like parabolas, sort of, but in between them there's actually a vertical asymptote. So these things do not spread outward forever. They almost go vertical. Not quite. They're still slightly curved, but you know how asymptotes work. It's like a barrier that the line or graph never crosses. So in between each one of these, and if I zoom way out, you're going to see there's infinitely many of them. So yeah, this is a very unique looking graph. But what's interesting is, now remember, secant is the reciprocal of cosine, or cosine is the reciprocal of secant. Watch what happens if I graph this exact same thing, but I use the cosine instead. So I'm going to keep everything else the same. 2x plus pi over 6 minus 2. Look at how those two graphs connect. Look at the relationship between them. Now, that's not a coincidence. They go together like that. That's the mathematical property that they have. So the maximum and minimum points of the wave correlate to the maximum and minimum points of the secant, whatever you want to call that graph. So, and it goes on forever like that. So secant has a period length. It has a phase shift. It has a vertical shift. It does not technically have an amplitude. An amplitude is the distance from the center of a wave to the top, or from the center to the bottom. But if you look at the number in the normal amplitude spot, which here is 3, well, if you double that, 6, that's the distance between the maximum and minimums. Here, let me deactivate that graph. So this graph goes from up here, 1, down here, -5. The distance from 1 to -5 is 6, or twice 3, double 3. So that number doesn't have a specific name like amplitude, but it does sort of tell you how spread apart these maximum and minimum points are on that graph. So as far as what we're going to do here is we're going to try our best to draw it, and we're going to talk about the period length, phase shift, vertical shift. So let's do that first. Period length, PL, same thing, 2 pi divided by this number. 2 pi divided by 2 is pi, so the period length is pi. Phase shift, I'm going to set everything in parentheses equal to 0 and solve it. Subtract pi over 6, subtract pi over 6. 2 theta equals -pi over 6. Divide by 2. Divide by 2 is the same as multiply by 1/2. We get -pi over 12, which means this has a phase shift of being left pi over 12 units. So period length pi, the phase shift is left pi over 12 units. Vertical shift, that's the easy one. Usually I do the easy ones first, but vertical shift is that number. So there we have it. So I could go to -2 and draw a little dotted line. If I were drawing a wave, that line would help. It doesn't help as much in this context. It does kind of tell you where, we're going to have some of those little parabola type shapes up there and some down here, and you see we got a distance of 3 units in between there. But yeah, this you can or can't draw. It's up to you. As far as drawing these, it's kind of like before. You just kind of do your best. So we have a y-intercept, and we have that kind of like so. We have down here at 5 pi over 12 and -5. So where the heck is 5 pi over 12? Well, 6 pi over 12, 6 over 12 is 1/2. So we're just a little bit short of 1/2. That'd be right around here. And we've got this shape. Next one is at 11 pi over 12. Well, 12 pi over 12. 12 over 12 would be 1 pi, which is here. So we're just a little bit short of that. Now, I'm kind of being sloppy. I really spread that out too far. So there we go. This is one of those where I'm just going to ask you to do your best to approximate this as good as you can. 17 pi over 12. Well, let's see. 18 over 12 would be 3/2. 3/2 is right here. -5. So if I just move over a little bit, we've got this one. And then just short of 2 pi, 23 pi over 12. So 24 over 12 would be 2 pi. 23 over 12 would be just a little bit short of that. And we get kind of like this. So not pretty, but not bad. So there it is. In between each one of these, there are asymptotes. You could sketch those in if you want to. Interesting to try to determine exactly the value of those asymptotes. We're not going to worry about that right now. But there we have it. So there's a secant graph. Let's look at number 10. Number 10 is a cosecant graph. Is there only one? Yeah, so you're going to do 2 secants for homework. Number 10 is a cosecant graph. I did not give myself very much room, but that's okay. All right, so the analysis. Amplitude, there is no such thing. Period length, 2 pi over 1/3, which when you flip and multiply is 6 pi. Phase shift. Phase shift, you take theta over 3 minus 5 pi over 6, set it equal to 0. Theta over 3 is going to equal positive 5 pi over 6. Multiply both sides by 3. That's 15 pi over 6. 15 over 6 reduces by 3, so that's 5 pi over 2. So right, because it's positive, right 5 pi over 2, that's the phase shift, period length. The vertical shift, there is no number added, not in the front, not in the back. So as far as vertical shift, there is none. And I just realized that back on number 8, I never actually went down to check my work. So let's see, pi, left pi over 12, and negative 2. Pi, left pi over 2, down. Okay, so they use the word down for vertical shift. I just wrote negative 2, but that's the same thing. Hopefully that's not a problem. Let's check number 10 while I'm at it. 6 pi, right 5 pi over 2. So number 10, 6 pi, right 5 pi over 2, and then none. And now we need to try to get this graph. So let me clear these off. Y equals 1/2 function cosecant x over 3 minus 5 pi over 6. And wow, let me hit the home button. So that's a very interesting look. My graph paper goes all the way to 9 pi, so I need to make this sort of fit to 9 pi. Well, it was cooperating. There we go. 10 pi. It's pretty close. And just for kicks, remember cosecant is the reciprocal of sine. So if I were to graph 1/2 function sine, and you don't have to do this, I'm just doing this because it's oh so gosh darn interesting, minus 5 pi over 6. You see that that wave does fit in between those sort of parabolic type shapes there. There are once again asymptotes that separate those red shapes, but the wave connects the maximum and minimums like that. And so just kind of the interesting relationship. Okay, so let me shut that off and we will do our best to graph this. So we have a y-intercept 0, -1, and then at pi, and then -0.5. And then with a little symmetry, I can do this. This next one has a vertex at 4 pi 1/2. And it's kind of like, well, okay, that's a bad, horrible drawing. So it kind of goes up. Now, I'm real curious at where those asymptotes are. Where do you think those asymptotes are? Halfway between 2 pi and 3 pi. So right about there is if we're really trying to get picky on this and do it right. So between, let's see, this graph, which I only drew half of, and then the next one, which is 7 pi -0.5, halfway between 5 pi and 6 pi. Halfway between 5 pi and 6 pi. Looks like there's an asymptote there. I suppose I could have done this on the previous problem. I just really wasn't thinking of it at the time. And then, is there anything else that'll fit on this graph? There's sort of like the tail end of one of those curves. Put little arrowheads on there. Yeah, I got them. And there it is. There's our graph. So these can be a real challenge to draw. Again, you tap the points on the screen. You can correlate them to points on your graph paper. Manipulate the screen to get it to fit a way that makes sense to you. If in doubt, like on this other problem up here, I didn't know exactly where to plot those points. But you kind of just say, well, it's just to the left of this or just to the right of that, and you just sort of make an estimate and draw your graph. I realized that I drew in those asymptotes. You do not have to do that. If you do, you get an extra gold star, but you don't have to. Here, I left this one out, but right there would be. Okay, so do your best to do these. Let's see, graphing on Desmos here, up there. It doesn't look like there's a terrific amount of space here. If you're working on your iPad, of course, you can zoom in, give yourself more room to work. You can shrink, to fit. if you need to, where you use the scissors, circle this, shrink it down, do things like that. If you're working on paper, feel free to certainly spread this out and do whatever you need to do. Show your work. And yeah, good luck with these. If you have questions, post comments or email me, and I'll be happy to help. So have a great day. Bye.